Yes, Nina, it is a problem solving session, and you can ask your doubts. It is possible for me so that I will try to clear your doubt. So through problem solving, I can able to clear your doubt. I think like this. So yeah, okay. Let's start the session. Hello everyone, a very good evening to all of you. So yeah, my name is Pooja Verma. I'm PMR Research Scholar from IIT Kharagpur, and instructor for this course is Professor M.K. Bhuvan, Department of Electronics and Electrical Engineering from IIT Guwahati. This is a live and interactive session of computer vision and image processing fundamentals and applications. So I hope all of you have gone through this week video lecture. This is a week 3, and also you can confirm me whether I'm audible and visible. Okay, so you can use chat box for asking and interacting. This is a live interactive session, so try to interact during the questions. Okay, so this is a week 3. So again, we will go through some concepts and some numerical problem related to the image formation. Already we have gone through some questions, so we will solve here some more questions. Okay, so these are some textbooks and references that have been used for this course. And this is our first question. The first question for this week is, which of the following matrices contain an intrinsic parameter of the camera? So options are rotation matrix, calibration matrix, option C is translation vector, and option D is fundamental matrix. Which option is the correct one? Okay, option B or option C. Okay, others, what about others? Please try to give answer, then we will discuss here in detail. Okay. Mm. Okay, so let's see the solution for detailed solution for this question. So our option A is a rotation matrix. So rotation matrix is a extrinsic parameter, not an intrinsic parameter. It basically describes the camera's orientation relative to the world coordinate system. So that's why it is a extrinsic parameter, not an intrinsic parameter. And the calibration matrix, it represents the intrinsic parameters that encodes the internal parameter of the camera that are the unique for to its hardware and don't change of where the camera positions in the space. So intrinsic and the calibration matrix basically includes the focal length, principal point, and skew coefficient. So what is a focal length? So focal length basically the distance between the lens and the image sensor that typically expressed or represented by the pixel unit. And the principal points that is the px and py that is the pixel coordinates where the optical axis intersects the image plane. Okay, and the skew coefficient basically it accounts for the any non-orthogonality between the x and y axis of the sensor. And the other parameter is translation vector. So this is also the extrinsic parameter, not an intrinsic parameter. So it describes the camera's physical position, that is basically location in the 3D world. And the fundamental matrix basically it represents or it relates metrics related to points between the two different camera views. Okay. Basically, it depends on the intrinsic parameter of the both camera. It is not a matrix that contains the intrinsic of the single camera. So rather, it represents the geometric constant between the two images. So the very correct option is option B, that is a calibration matrix. Okay, so option B is the correct answer for this question. Which of the following matrices contains the intrinsic parameter of the camera? So intrinsic parameter that contains all the parameters, that is a calibration matrix. Okay, have you understand? Okay, so now moving to our next question. Our next question is in the intrinsic parameter matrix, what does the skew coefficient typically represent? Option A, the distortion of the lens. Option B, the angle between the x and y pixel axis. Or option C, the distance between the lens and the image plane. Or option D, the rotation of the camera. So would you like to try for this question as well? Which option can be a correct one? In the intrinsic parameter matrix, what does the skew coefficient typically represent? The distortion of the lens, the angle between the x and y pixel axis, the distance between the lens and image plane, or the rotation of the camera. Please try for this question. Try to answer for this question. Which option can be a correct one? At least try. Then we will discuss in detail. Okay, B. Okay, so let's see the detailed solution for this question. So here our option A is the distortion of the lens. So basically the distortion of the lens represents the distortion coefficient, that is the radial or and tangential. So which are the distinct from the linear transformation of the intrinsic matrix. So it is not a representation for the skew coefficient. And the another one is the angle between the x and y pixel axis. So the skew coefficient basically in the intrinsic camera matrix represents the or non-orthogonality of the x and y axis of the image sensor. Already we have seen in the previous slides as well. So specifically it is a function of the angle alpha between these axes, and it is defined as fx cot alpha. Okay, so in an ideal camera, the pixel axes are perfectly perpendicular. That is alpha is equal to 90 degree in that case, making that makes the skew coefficient 0. And our third option was the distance between the lens and the image plane. So this describes the focal length f, where the intrinsic parameter but not a skew coefficient. So it represents the intrinsic parameter, not a skew coefficient. And the rotation of the camera. So this is the extrinsic parameter that describes the camera orientation in the world coordinate system, not a internal sensor geometry. So correct option is the angle between the x and y pixel in the axis is the correct option for this question. Okay. So basically the skew coefficient represents the angle between the x and y pixels by equation fx cot alpha, where if alpha is 90 degree, that makes the skew coefficient 0. Okay. Now moving to our next question, how many degree of freedom does the extrinsic parameter set have? Okay, here again B. Okay, around. Let's see. Anyone else who wants to give answer for this question? The question is how many degree of freedom does the extrinsic parameter set have? Okay, 6. Okay, so let's see the solution for this one. So in the extrinsic parameter that describes the camera pose in the word, the extrinsic parameter. Okay, we will see now. Yes, that is C. So the basically extrinsic parameters that defines the transformation between the two coordinate system, that is the word coordinate system and the camera coordinate system. So a rigid body in the 3D space possesses 6 degree of freedom because the full pose is determined by the two independent component, that is a three translation degree of freedom, that these represent the movement along the x, y, and z axis, and the translation vector is defined as t is equal to tx, ty, tz of transpose, and the three rotation degree of freedom. So these represents a rotation around these three axes, and and often expressed as a Euler angle, that is a roll, pitch, and yaw, or a rotation matrix. So basically, we have 6 degree of freedom for the extrinsic parameter, 3 for the translation, and 3 for the rotation. Okay. So although the rotation matrix has 9 elements and they are subject to the 6 orthogonality constant, leaving only the 3 independent parameters. So that is combined with the translation parameters at total extrinsic set has 3 plus 3, 6 degree of freedom. So correct option is 6. Okay. So extrinsic parameter set have 6 degree of freedom, 3 for translation and 3 for rotation. So now moving to our next question. So our next question is, given a word point that is a PW 10, 10 and 10 transpose, the camera is at the origin but rotated 90 degree around the z-axis. Here overall rotation matrix itself it is given. What is the coordinate in the camera frame? So if we ignore, it is giving ignoring the translation. So what is the coordinate in the camera frame? So how to solve this question? Anyone want to try for this question? What will be the answer? Here the word point is given and it is also given the camera is at a origin but rotated 90 degree around the z-axis. So here 90 degree rotation with the z-axis, the matrix is given. Now we need to find the coordinate in the camera frame. Okay, B. So yeah, how it can be a B? You are just guessing or giving the answer? Okay, rotation matrix. Okay, okay. Yeah, that's correct. But not exactly in that. So yeah, we will see. So basically to find the coordinates of a point in a camera frame, that is a PC, you can say that. So given its word coordinate PW, so what how we can, so we use the inverse of the camera's orientation. Here since R is the orthogonal, okay, we will see, we are solving here. Okay, try to solve with me this question. So here rotation R and around the Z axis rotation it is given, and overall rotation matrix it is given. So what is equation that is related to the point in the camera frame and the word frame, coordinates in word frame? So the equation is PC, that is point in the camera frame, is equal to R transpose, where R is the rotation matrix, and PW minus T. And here we know that PW is the word point coordinates, and T is the translation vector, right? Translation vector. But here they have said that ignore the translation. So that means T is equal to 0 here. So equation will be T is equal to R transpose PW, right? Okay, so here already they have, so this is transpose matrix overall rotated matrix it is given. So we can take it directly. Okay, so that is a rotated already. It is rotated around 90 degree. This matrix it is given. So we don't need to just transpose it. Okay, so here 0 minus 1 0 1 0 0 0 0 1. This is our rotated matrix, and our PW is the word points are 10, 10, and 10, right? So if you just multiply to by column, so 0 minus 10, so here minus 10, again it all the other two only ones are there, so 10 and 10, right? So if you write it, you can write it minus 10, 10, and 10 transpose. So yeah, this is option B is the correct answer for this question. Okay, so here already in the question, rotated z around 90 degree it is given. So don't need to just transpose it. Already it is given. Okay, so yeah, option B is the correct answer for this question. So have you understand this question? Is it fine? Can we move to our next question? Can we move? Okay, so that's what I was telling. Rotated around the z axis, it is already given. So that's why we don't need to rotate it. I mean, we don't need to transpose it. It is already given, rotated around the z-axis. So what they are asking, just transpose of the rotation matrix. So already it is given in the question. So here, that's why we don't need to transpose it. Okay. Otherwise, it is given only, I mean, R matrix. That means rotation matrix. It is already written, rotated around the z-axis. So it is given. So it is a transpose matrix itself given in the question. Okay. Is it fine, Minal? Okay. Okay. So now moving to our next question. Our next question is, a stereo camera system has a focal length f is equal to 500 pixels and a baseline b is 20 centimeter. If the disparity of a corresponding point d is 50 pixels, what is the depth z of the object? So anyone have any idea how to solve this? So I think you must be gone through this type of question. So what would be the formula here we need to put? Yeah, correct. So can you put all the values and let me know what will be the answer for this question? Yeah, this one is a formula is correct. Depth is equal to F into B divided by D. So where B is the baseline, F is the focal length, and D is the disparity, right? Okay, yeah, correct. We have given the right answer. So let's solve here for others. Yeah, B is the correct answer for this question. So as we know that Okay. So as we know that the relation between the relation between depth, baseline, focal length, that is F, and disparity, that is B, is defined by this equation. Z is equal to F into B divided by D, where D is disparity, F is focal length, B disparity is B. B is the baseline. It is a baseline, depth is Z, focal length is F, already it is given here. So here in the question itself it is given, F is given 500 pixels, right? Baseline B is given 20 centimeter and D, that is disparity, is given 50 pixels. Now just we need to put in this formula and then you will get the answer. So 500 F it is given and B is 20 centimeter divided by 50 pixels. So pixels will be the cancel out. So here 10. Overall you will get 200 centimeter, right? Z is equal to 200 centimeter. So yeah, option B is the correct answer for this question. Okay. Now moving to our next question. Our next question is, an object is moving away from the stereo camera at time t1. Its disparity is 60 pixels and at time t2 its disparity is 30 pixels. How has the depth of an object changed? Option A, the depth has doubled. Option B, the depth has halved. Or option C, the depth has increased by 30 centimeters. Or the depth remains unchanged. So, can you answer? Already we know that the relation between the disparity, focal length, and baseline depth, right?
It will double.
Okay, it will double. Okay, how?
Uh, the object depth is inversely proportional to the disparity. So
Correct.
that's why.
Yeah, correct.
So it will be like 60 upon 30.
Yeah, that's correct. So, yeah, here detail. Okay, so already we know that in a stereo vision system, the relation between the depth and disparity, I'm just writing here, in stereo vision, the relation between depth, that is Z, and disparity, D, is inversely proportional, right? Proportional. And already we have seen the formula in the previous question as well, that is Z is equal to F into B divided by D. So we can write it like Z is inversely proportional to D, and we can take as a constant itself. It let's C is equal to FB. Let's assume that assume that. So we can write it from here. Z is equal to C by D, where C is a constant, C is equal to F into D, right? So here it is given at time t1, its disparity is 60 pixels, right? So at time t1, let's say it is a z1 because we need to find the relation between the, I mean, how the depth will be the double. So just we need to check depth and disparity equation only. So let's say at time t1, the depth is z1. So we can see by that time the disparity is 60 pixels, right? And at time t2, it's z2. So see by 30 pixels, right? So if we just take a ratio between the at time t1 to t2, how the objects will be changed. So z2 divided by z1. So z2 is c by 30 and z1 is c by 60. So here we'll get 60 by 30. It is 2, right? So depth will be the double. So as like an object is moving away from the stereo camera. So at time t2, in the first time t2, the disparity is 60 pixels, and at time t2, the disparity is 30 pixels. So how has the depth of an object is changed from t2, t1 to t2, right? Like objects is moving like this. Here it is a t1, here it is a t2. Let's assume that. Okay, so how the depth of an object has changed from the T2 to T1. So this is the depth has doubled. Okay, so option A is the correct answer here. Is it fine to all of you? Can we move to our next question? Okay, so moving to our next question. Now next question is a point in word coordinate system is PW, that is given as 10, 20 and 5. The camera is translated by a vector t, that is it is given here, that is -5, 5 and 10 relative to the word origin, that is a no rotation. What are the coordinates of the point in a camera coordinate system PC? Here we need to assume PC is equal to PW plus T for pure translation. Okay, here already in the question it is given as no rotation. So that's why the rotation R transpose is not there. So can you calculate here? Already PW is given, T is given. So just can you calculate it here? Already we know that the relation between the word coordinate system and camera coordinate system, like PC is equal to R transpose PW T, right? The formula is PC is equal to R transpose PW plus T. Here T is the translation vector. Here R transpose is a rotation and PW is a word coordinate system and PC is the camera coordinate. So here no rotation, so that means that is not performed. You can say that it is 1. So here it is also given. If for pure translation, the equation will be the PC is equal to PW plus T. So PW itself it is given here. T is also given here. So PW is 10, 25 plus the translation vector is also given minus 5, 5 and 10. So just a two matrix. So we can just add this 10 plus or yeah, minus. So 5, 25 and 15, right? Or we can write it 5, 25 and 15 transpose, right? So the coordinate of the point in the camera coordinate system is 5, 25 and 15 transpose. So which option is the correct one? Option A is the correct answer for this question. Yeah, 5, 25, 15. Yeah. Is it fine, everyone? So yeah, I hope it's an easy one. So moving to our next question now. The next question is a 3D point in a camera coordinate system is it is given PC 20 minus 10 100. The camera has a focal length f is equal to 500 pixels and principal point that is a cx and a cy. It is also 320 and 240. What is the q that is a horizontal pixel coordinate of this point in the image? So how to solve this question? Anyone have any idea how to move? So here PC is given, principal point Cx and Cy is given, and focal length f is given.
And
And yes, how to proceed with this question? Any idea?
100.
Yes. No. How to proceed with this question? You know the formula. So a 3D point like P is given, the XYZ in the camera coordinate system that is projected onto a 2D image plane. So the horizontal pixel coordinate that is a U is calculated using the focal length fx and the principal point axis cx and the cy that is related to this is a horizontal pixel coordinate. It is represented by fx into x by z plus cx. If it is given that vertical pixel coordinate, so it is also like given as v f. Here you can f is the focal length, y divided by z plus c y. It is represented by this one. And just I can write it here. 3D point, 3D point, let's say P, X, Y, Z in the camera coordinate system is projected onto the 2D image plane Then the horizontal pixel coordinate U is calculated by focal length principal points, that is Cx and Cy. It depends on the horizontal or vertical you are calculating, and depth, that is Z, using this equation. Okay, so already all values are given, right? X, that is given 20 here. Z is, it is a 100 here. Focal length f is 500 pixels and the Cx is 320. So we need to just put in this equation. So f is 500 into 20x and z is 100 plus 3x, that is 320. So if you calculate it here, so 100 plus 320, overall you will get 420. Okay, so this is a pixel coordinate of this point in the image, that is a 420. So option B is the correct answer for this question. So it is a multiplication here. Okay, so have you got this question? Is it fine? Okay, I hope all of you have understand this question. Now moving to our next question. So our next question is, using the big perspective model, an object has an average depth, that is Z average is 2000 millimeter, and the camera focal length is 50 millimeter. If a feature on the object is 100 millimeter tall, in the real world, how tall will it appear in the image in millimeters? Anyone have any idea how to proceed with this question? So here, using the weak perspective model, an object has an average depth is given 2000 millimeter. The camera focal length is 50 millimeter. If a feature on the object is 100 millimeter tall in the real world, how tall will it appear in the image? Okay, so let's solve this question. So in the weak perspective model, it is assumed that all points on an object are at a constant average depth, that is already it is given Z from the camera. It is assumed that. So the magnification M is a uniform across the object, and that is calculated by the ratio of focal length to the average depth. So you can write it here in the weak perspective model. it is assumed that all points on an object are at a constant average depth, that is a Z average, from the camera. Camera. So the magnification M is uniform across the object and it is calculated by this equation, that is M is equal to F by Z average. Okay, so this is the magnification. First, we will calculate the magnification. So F, that is focal length, it is given 50 and Z average is given 2000, right? So 1 by 40, so overall you will get 0.025, right? Here. So now to find the height of the feature in the image, H multiply with the real world height by the magnification factor. Okay, so to find the height of the feature in the image, let's say image H, it is written. So we need to multiply the real world height. So real world height, it is represented by the capital H by the magnification factor, that is M. So I'm just writing it here. So the image height, that is H, is represented by real world height into magnification factor. Okay. So real world height of an object feature is, it is 100 millimeter. So 100 and magnification factor that we have got 0.025. If you multiply it, you will get 2.5 millimeter. Okay, here. So the feature will appear 2.5 millimeter tall in the image. Okay. So if the feature on the object is 100 millimeter tall in the real world, so how tall will it appear in the image? So 2.5 millimeter tall it will appear in the image. So option A is the correct answer for this question. Okay. Is it fine to all of you? Have you understand this question? Is it fine? Can we move to our next question? Okay. So now moving to our next question. Our next question is, consider a circular object defined by fxy is 5 inside a radius r is equal to 4 and 0 outside. Calculate the radon transform value, that is z rho theta, for rho is equal to 0, a line passing through a center. So we need to calculate the radon transform value z rho theta. A function is given, object defined by a, and radius r is given. We need to calculate for rho is equal to 0. Inside radius is 4 and outside radius is 0. So how to solve this question? Okay, so have you gone through the Redon transform? Okay, so let's see it here. So the Redon transform, that is g rho theta, represents a line integral of a function f(x,y), that is this one, belong along a straight line defined by the parameter rho, that is distance from the origin. Someone is okay, 80, someone is answering, okay, we'll see. Okay, so I can write it here also. The Redon transform g rho theta is represent the line integral of a function f(x,y), that is given along a straight line that is defined by the parameter rho. It is in general it is defined here, but for our question we need to change it. Okay, here rho. So it is a distance from origin, and theta, that is a angle of the normal to the line. Angle of the normal to the line. So for a line passing through the center, that is rho is equal to 0. So the overall integral is given by, that is g rho theta, that is minus infinity infinite, f s cos theta plus pi by 2, comma s cos, here it is a sine theta plus pi by 2 ds. This is the overall integral of the Redon transform. So here overall function, that is it is a x, it is represented by x, it is a y. Okay. So here it is given, since the consider object is a circular object, and that is defined by the fxy is equal to 5. Okay, so here since the object is uniform circular disk with the radius r is equal to 4 for inside and outside for 0, so the constant value fxy function is given as a 5. So any line passing through the center, that is rho is equal to 0, is simply a diameter of the circle, because the object is rotationally symmetric and the result is independent of the angle theta. Okay, so that will limit the integration that is defined by the boundaries of the disk along the line, that is range from a specific, like range of that radius. So g rho is 0 here, and theta. So angle is also, that is not dependent on the angle. So just take it as a constant. So I just write it here 0 theta, and it will be the defined then radius minus r to r, because it is a circular object. Okay. So here f, let's say it's x, y in that one into ds. Okay. So here, so r, it is a radius, that is inside radius is minus 4 to 4, function that is given the constant value, that is 5 ds. Okay, 5 ds. If you integrate it with respect to ds, so what we will get, 5, that will vary minus 4 to 4, right? It will vary 5, as you can say that if you put here 5, 4 minus of minus 4, so you will get 5 into 8. So overall you will get 40 here. Okay, not 80. Just put in this equation, taking it as a constant. Here it is because of circular object, that radius is 4. So for a circular object, a constant value for the function it is given. Just put in that one, and it is radius. So it is overall value for any other function. So for this one, we are taking the radius. So minus r to r, it will be vary. Okay, and for line passing through the center, so that this equation became this one, and if you integrate with respect to you will get this one. So have you understand, or I can just write it from here clearly so that it will clear to all of you. Okay, so if you do the integration here, so overall you will get 5 here with respect to integrating the s, so minus 4 to 4, right? If you do the simple integration, so this is the value. So if you just add it, 5 into 8, so 40. So this one is 40 is the answer. So option C is the correct answer for this question. Is it fine? So it is a circular object. It is defined a common function. It is overall. Okay? Is it fine? It is a circular object. So circular have a radius only. So that's why inside radius is given as r is equal to 4. So that will vary minus 4 to 4 only, right? It is a circular object. That's why we are taking. So is it fine? All of you? Can we move to our next question? Okay, so moving to our next question. Now next question, now it is related to the previous one. For the same object, that is question 10, that is a circular object is there. So let's say amplitude A is equal to 5, radius R is 4. Now we need to calculate the radon transform value at distance rho is equal to 3 from the center. So previously what we have done, rho is equal to 0, that is line passing through the center. Now we need to calculate the rho is equal to 3 from the center where the rho is defined. Okay, and here the amplitude of that same object and radius it is also given. So now how we calculate this one? Okay, B already is giving answer. So how we can calculate this one? So already we know that the radon
And this is
trans
also
circle. This is also a circle.
Yes.
So I used this formula 2a into square root of r square minus rho square. So in integration, if you go for circle also, after applying limits, we get the final value. So in this, if we substitute, I'm getting 10 root 7. 2a into square root of r square minus rho square.
Yeah, yeah, correct, correct. So yeah, this one is correct. What he is telling, because it is a circular object, and here rho is defined. Here rho is not equal to 0. So we need to
Yes.
put it in this integration, then you will get it. Okay. So if we just previously, if we just go with this equation, here rho is equal to 3 and amplitude is also given for this. So now in this integration will vary r square minus rho square root of, and here it is also r square plus rho square. No, here it is a minus, and here amplitude of this given a d z or ds, whatever you can take. Okay, so if you just integrate it, so you will get 2a root of r square minus rho square, right? You will get it. Now here amplitude is given, r square is given. So for g, rho is 3 and theta value. So a is 5, so 2 into 5 in root r square minus rho square. So r square is 4 square and rho is minus of 3 square. So 2 into 5, 16 minus 9. So yeah, 10 root of 7 you will get. Okay, just put in the previous one the main formula, you will get it. The object is circular, but here the distance rho is given, it is a 3, amplitude is also given here, so that's why this equation will become this one. Okay, so 10 root 7 for this one. So yeah, option B is the correct answer for this question. Is it fine, all of you? Just we need to put in the previous equation. This here, it is not a line passing through the center where rho is equal to 3, value is given, and amplitude is also given. So just put in the place of fxy a, amplitude it is there, and just make an integration and put the values of r square and rho square, and you will get the answer for this question. Okay, so I hope all of you have understand this question. So now moving to our next question. So our next question is, according to the Fourier slice theorem, if the projection of an object 0 has a total area that is integral of 50, what is the value of the 2D Fourier transform, that is GUV, at the origin 0, 0? So anyone have any idea? Will be the value of at the origin 0, 0. Okay, so the Fourier slice theorem that states that the Fourier slice theorem states that the 1D Fourier transform of a projection, let's say it's a state of omega, is a slice of the 2D Fourier transform. Fourier transform FUV. So at the origin, already we know that DC component, or we know that DC component frequency is equal to 0, right? And the Fourier transform represents the sum of the signal. Transform represents the sum of the signal, right? At the origin, where all the components, where it is Fourier transform basically represents the sum of all the signals, right? In normal Fourier transform also, so if all the values is 0, 0, then 0, 0. So since the integral area is given as a 50, here it is 0. The value at the origin will be the 50 because it is the sum of all the signals. So here if this value it is given as a 50, so here no value is defined. So the origin value will be the 50 only, right? Since the integral, that is area, is given as 50, so the value at the origin is 50 only. Okay, so option C is the correct answer for this question. So in the Fourier slice theorem, that states that 1D Fourier transform of a projection is a slice of the 2D Fourier transform. So at the origin, already we know that in the Fourier transform, if you have gone through the previous one, the Fourier transform at the origin, that represents the sum of all the signals. So it is already given the total area of an object. Here it is given, that is 50. So since the overall integral value is given 50, so the value at the origin is 50 only. Okay, so option C is the correct answer for this question. So yeah, have you understand this question? Is it fine, all of you? Okay, so now moving to our next question. Now next question is theoretical one. What is an epipole? So option A center of the image. Option B, the intersection of the optical axis with the image plane. Or option C, the image of the other camera's optical center. Or option D, the points where all light rays converge. Which option is correct? Now I think if people can give the answers. Try to answer for this question. What is epipole? It is a basic simple question. B, most of you are saying that option B is the correct answer. Okay, so let's see the detailed solution here. So first we will go through the each options, then we will see which one is the correct answer. Okay, so option A is the center of the image. So basically the center of the image is the point where typically we call the principal point, right? Px and Py already we have in that. That is the principal points of an image, and that is also center of the image. So basically, an epipole can be at a center if the cameras are moving directly towards each other and along the optical axis. So it is not a definition of an epipole, so that is not a correct option. Option A is not a correct option. So the intersection of the optical axis with the image plane. So this is a specific definition of the principal point, not an epipole. So this is also not a correct option. So now next option is option C, that is the image of the other camera's optical center. So in the epipolar geometry, which describes the relationship between the two cameras viewing the same scene. So an epipole is the point of the intersection between the line connecting with of the two camera center, that is called the baseline, and the image plane. So because this baseline passes through the both optical center, the epipole in one image is effectively the projection or the image of the other camera's optical center into that view. So this one is a correct option for this question, because this is a definition, or this is a basic definition of the epipole. So have you understand what is a epipole? Basically, it describes the relationship between the two cameras that is viewing at the same scene. Okay. An epipole, that is the point of the intersection between the line connecting the two cameras centers and the image plane. Okay, so this is the correct definition for the epipole. And the last one is our the point where all light rays converge. So this that is describes the optical center or a center of the projection, so which is the 3D point in space rather than point in the image plane. Okay, so the correct option is C, the image of the other camera's optical center. So option C is the correct answer for this question. The epipole is the image of the other camera's optical center. Okay, okay, so I hope you have understand this question. So now moving to our next question. Now next question is, if two cameras are rectified, uh, standard stereo setup, where are the epipoles located? Option A, at the center of the image. Option B, at the corner of the image. Option C, at infinity. Or option D, at a principal point. Someone is giving answer. Okay, option C. If two cameras are rectified, standard stereo setup, where are the epipoles located? Anyone else who want to give answer for this question?
It will be at the infinity.
Yeah, it will be at infinity only. Yeah. Okay, so let's see the detailed solution here. So we will go option by option, then we will check which option is the correct one. So at the center of the image. So that would be only happens if one camera was directly looking at the optical center of the other along its own optical axis, which is not a case of standard parallel rectified setup. So it is not a correct option at the center of the image and at the corners of the image. So epipoles are not restricted to image corners, so their positions depend on entirely on the relative translation and rotation of the cameras. So it is also not a correct option. And now next option is at infinity. So in a rectified stereo setup, the two cameras are oriented such that their image planes are co-planar and their optical axes are parallel to each other. Okay, so their basically parallel baseline. So epipoles is defined as the projection of the one camera center onto the image plane of the other camera. So there will be the no intersection. That means that are the parallel. So because image planes are in the parallel, so the line connecting to the camera center, that baseline never intersect of the image plane at any infinite point. So that results consequently the epipoles located at the infinity. Okay. So this geometry ensure that all epipolar lines are the parallel to each other and that typically align with the horizontal image axis x-axis and simplify the search matching point to the 1D horizontal scan. This one is the correct option for this question. So last one we will see at the principal point. So the principal point is where the optical axis intersects of the image plane and the rectified setup. The optical axes are the parallel and don't pass through the other camera's center. So the epipole cannot be the principal point. So the correct option is at infinity. That is option C. So option C is the correct answer for this question. Now moving to our next question. Now next question is also related to this one only. Epipolar constant. So the epipolar constant reviews the search for the corresponding point from a 2D region to. So option A is a single point, option B a 1D line, or option A C is a 3D plane, or option D is a circle. Which option is the correct one? Okay, some of you have answered as well. Okay, option B a 1D line. Okay, so let's see the solution here. We will go option by option. Yeah, option B is the correct answer. Nice, most of you have given the correct answer. So the explanation, let's see the up for option A single point. So the epipolar constant alone cannot be identified the exact point because of the depth of the 3D point is unknown. So it only knows the point lies somewhere along the projected area or in the line. So that cannot be a correct answer for that question. So option B, a 1D line. So the epipolar constant is a fundamental principle in the stereo vision that dictate that for a given point in a one image, its corresponding point in another image must lie on the specific line. That is called the epipolar line. So they're used for dimensionality reduction. So in the standard search for the correspondences, one might theoretical search an entire 2D region, and for the geometric constant, because of the 3D point, the two cameras center and the image projections all lie on the same epipolar line. That such space is restricted to the intersection of this plane and the with the image sensor, which is also a 1D line, and that will reduce the computational complexity of the image matching from the O of n to here n square, which is to O of complexity of the n along the scan line. And our option C is the 3D plane. So while the constant is derived from the epipolar line in the 3D space, the search is corresponding point happens in the 2D plane. So where the 3D plane manifests as a 1D line, not a 3D plane. Okay. So a circle that under a standard pinhole camera model, the intersection of the epipolar line and the image plane is a straight line, not a circle. So the correct option for this one, option B, that is a 1D line, is the correct answer. So the epipolar constant reduces the search for a corresponding point from the 2D region to a 1D line. Okay. Okay. So now moving to our next question. Our next question is in computerized tomography, the radon transform effectively maps an image from a spatial domain XY to frequency domain UV. Option B is projection domain rho and theta. Option C, the time domain T, or a color space RGB. Which option can be a correct one? Option B. So in computerized tomography, the radon transform effectively maps an image from a spatial domain to which domain? Any other who want to give answer for this question? Okay, so let's see the explanation it is given here. So in computerized tomography, the radon transform represents the mathematical process of mapping a 2D image from a spatial domain to a projection domain, and also known as the sinogram. So this transform computes the line integral of the image density along various angles theta and distance rho from the origin, and that represents the data collected by the CT scanner. So in the spatial domain XY, the origin image represented attenuation coefficient of the tissue, and in the projection domain, the resulting sinogram where theta is the angle and rho is the perpendicular distance, and that is also called a radon space. So the correct choice is option B, that is a projection domain. That is option B. So in the CT, computerized tomography, the radon transform effectively maps an image from the spatial domain to a projection domain. Okay, so I hope all of you are getting these questions. Is it fine, all of you? Okay, so now moving to our next question. The next question is, calculate the radon transform value, that is the rho theta for a point source fxy is equal to del of xy direct delta at origin for any rho is not equal to 0. So what will be the value for this one? Anyone? Okay, option A. So how we can calculate the radon transform value for the point source where the fxy is given as a del of xy for any rho is not equal to 0. Okay, so let's see there the solution it is already I have included. So in the radon transform already we have seen that z rho theta that represents the line integral of the 2D function, that is fxy along the line defined by x cos theta plus y sin theta is equal to rho, and that will be the mathematically then expressed by this one, our function here f rho theta. Basically we have defined it, this one, I mean g rho theta. So here double integral of minus infinite to infinite f of xy del rho minus x cos theta minus y sin theta dx dy, and we substitute the direct delta function at the origin, that is fxy, into this transform. If we put it, so using the shifting property of the direct delta function, then we will get here del of xy phi of xy dx dy, and we will get phi 0 0 because it is a direct delta function. So we have to evaluate the inner integral by setting x equal to 0 and y is equal to 0. If we put here, so we will get phi 0 0. So z rho theta, here we will get del of rho minus 0 cos theta and minus 0 sin theta. So overall we will get z del of rho. So that results of the transform of the 1D direct delta function 0 by this definition. So if rho is equal to 0, then function will be the infinite. If rho is not equal to 0, already we know that in the direct delta function it is will be the 0. So since this problem is explicitly states that rho is not equal to 0, so the value of the function is identically 0. Okay, and geometrically it occurs because of the line integration does not intersect of the point source located at the origin when the displacement rho is non-zero. So in the radon transform value will be the 0, which corresponds to option C. So yeah, option C is the correct answer. If rho is not equal to 0, then function, the return transform value will be the 0 only for a given point source fxy is equal to del of xy. Is it fine to all of you? Have you understand? Is it okay? This solution is okay for you? Okay, so now moving to our next question. So our next question is, in the weak perspective camera model, the scaling factor is option A, dependent on the depth of every individual point Zi, constant for all points in the object. Option C is randomly generated. Option D equal to the focal length. Okay, constant for all the points. Okay, we'll see. So let's see the solution here. So we will go option by option. Yeah, most of you. So whoever answer is the correct. Option B is the correct answer. So option A is dependent on the depth of every individual point Zi. So that describes the full perspective projection model where each point's image coordinates are divided by its unique depth Zi. And the constant for all the points in the object for this question, the weak perspective camera model, also known as a scaled orthographic projection, that simplifies the standard perspective model by assuming the depth variation of a point on an object are small relatively to their average distance from the camera. Already we have solved that question as well. In the image, it will the average distance is small relatively to. So in this model, basically in the constant for all points in the object. So for the perspective model, individual depth that is Zi for each point is replaced by a single average depth constant depth. And the scaling factor S is defined by the as a ratio of the camera focal length to this average distance, that is f divided by z dash, where z dash is z average basically, because z dash and f are the fixed entire object in a given frame, so scale factor remains the constant for all the points belonging to the object. So this option B is the correct answer. Now next our option is just C and D, randomly generated. So it is not a correct option. So scaling factor in a geometric camera model is derived from the physical or mathematical constant, so not a stochastic process, and equal to the focal length. While the focal length is a part of scaling numerator, so actual scale factor must account for the distance of the object, that is s is equal to f by z, not f by z dash. If it were only equal to the focal length, it would ignore the physical size reduction caused by the distance. So it should not be a correct one. So the correct option is option B, constant for all the ob- for all points in the object. So yeah, option B is the correct answer for this question. Now moving to our next question. Next question is, why is filtered back projection preferred over simple back projection? Option A, it is faster. Option B, simple back projection results in a blurry image. Or option C, it requires less memory. Option D, it works without a computer. Which option is the correct one? Why is filtered back projection preferred over simple back projection? Any guesses? Okay, so let's see the solution here. So option A, it is faster. Filter back projection is actually computationally more intensive than the simple back projection that requires the additional mathematical step of applying a convolution filter. It often uses the fast FFT, fast Fourier transform, to every projection before processing. So it is a faster, it is not a correct one. So simple back projection results in a blurry image. So in a filtered back projection, that is a standard analytics reconstructed algorithm used in CT imaging to overcome the significant limitation of the simple back projection. So one is one another major filtering mechanism. Simple back projection smear data across the image and results a blurry appearance, and artifacts where point sources appear as a blurred streaks. And now it's filtering mechanism. So FBP applies the mathematical filter, commonly high pass RAM filter, to a projection data before the back projected. So this filter effectively surpasses the low frequency components responsible for the blurry, leading much sharper and more accurate reconstruction. Actually, I think it is interchanged. So yeah, the correct option is option B. Simple back projection results a blurry image. So that's why here we are using a filtered back projection over the simple back projection. So now next option is it requires less memory. So FBP typically requires more memory, or at least a similar amount, because it must store the process filtered version of the xenograms in addition to a raw data. It requires more memory, not a less. And now next option is it works without a computer. So both methods are digital reconstruction technique that rely on the computers to process thousands of data points. So simple back projection was used in early analog experiments, but the clinical experiment implementation of either method requires the computational power. So that is also not a correct. So correct option is simple back propagation projection results in a blurry image. So option B is the correct answer. Why filtered back projection is preferred over a simple back projection. Okay. Now moving to our next question. If the disparity map in a stereo vision system is noisy, which of the following is least likely to improve depth estimation accuracy? Option A, smoothing the disparity map. Option B, increasing the baseline. Option C, using higher resolution cameras. Or option D, increasing the aperture size. Okay, option D. Anyone else? If the disparity map in a stereo vision system is noisy, which of the following is least likely to improve depth estimation accuracy? Any answer or any guesses? Anything?
Increasing the baseline.
Increasing the baseline. Okay. Okay. So let's see the solution here. So we will go again. I mean option by option. So option E is smoothing the disparity map. So applying the smoothing filter like median filter is a standard post-processing process. Already we know that steps removes outlier and noises from the initial disparity map, so thereby improving the overall stability and accuracy of the depth data. So the question is, if the disparity map is in the stereo vision system is noisy, which of the following is least likely to improve depth estimation accuracy? So here we need to improve the depth estimation accuracy. So that is also not a correct option. Now, next option is increasing the baseline. If we increase the baseline, so it should improve the disparity, improve the depth estimation accuracy. So increasing the baseline. A wider baseline distance between the two cameras increases the disparity for a given depth. This reduces the relative impact of the small pixel matching error, leading the overall lower overall range or It will remove the error, but not will increase, I think, accuracy that much. So now our next option is using the higher resolution cameras. So higher resolution cameras provides more detail and a smaller pixel size that allows us for final subpixel matching and reducing quantization error in the disparity calculation, and that will lead the more precise depth measurement, not for accuracy. Increasing the aperture size, while the larger aperture allows the more light into the camera, it significantly reduce the depth of the field. So this causes the object at a different distances to become a blur, and which degrades the sharpness of the feature needed to accurate stereo imaging. So in the stereo vision, crisp images features are essential calculate precise pixels corresponding to required a high quality disparity map. Okay, so in the stereo vision system with a noisy disparity map, if the disparity map is noisy, so the action likely to improve the depth estimation accuracy is the increasing the aperture size, not smoothing the disparity map. Or if we apply the median filter, so it will also blur, or it will not improve the accuracy. And also increasing the baseline, it lower the error absolutely, but not increasing, not improve the depth estimation accuracy. As well as using the higher resolution cameras is not a good option. So option D is the correct answer for this question, increasing the aperture size. Is it fine? How this answer is correct? Okay, so now again we will solve some numerical problem here. So already we have seen a lot of theoretically question. Now we will again some more numerical problem here based on the same concepts. Okay, so now the next question is, if you are observing an object at a depth of z is equal to 100 units, the disparity is d is equal to 20 pixels. If the disparity measurement changes by just 1 pixel, that is d 19 pixel here already, first is d is equal to 20 pixel. If we just change the measurement of disparity, just reduce by 1 pixel due to noise, what is the new calculated depth? So any one of you can just let me know. It is that formula also, relationship between the depth, disparity, focal length and baseline, right? So if we just change the disparity by the 1 pixel due to noise, then what will be the new depth? In 95 units, someone is asking.
105.26 units.
Yeah, correct. How you have calculated this one?
F, because it is inversely proportional to disparity. So I just made it 100 multiplied by 20 divided by 19. So
Okay, yeah, that is correct. So already we know that formula, that relation between the depth, disparity, focal length and baseline. So already all of you have know that. Well, it is Z. Z is equal to F into B divided by D, right? So here Z and T is given, right? So Z is equal to 100 and D is equal to 20 pixels initially. Now due to noise, if the pixel is just reduced by 1, then new pixel is 19. So just if you put here, if you make a relation, to Z into D is equal to FB. So let's say F and B are the constant, or directly you can calculate. So you will get here 2000, right? So now if the D is just like we can say that reduced by 1 pixel, so it is a 19, right here. So now to get the new calculated depth, that is Z new, you can say that FB already know that it is a 2000, right? FB. So 2000 FB, I can write it more correctly. So FB divided by D new, you can say that D new is our 19. So FB here, it is a 2000. D new is 19. So if you divide it, you will get 105.26. Yeah, that is the correct answer for this question. Okay. So here some conceptual ways and twist it is given. So just go with that type of questions only. We will able to solve. So now our next question is again based on that. So now you have a stereo ring with baseline B1 is 10 centimeter and that produces a disparity of the 12 pixels for an object. Now, if you want to increase the disparity to 36 pixels to improve matching accuracy, what should be a new baseline distance? So, how we can calculate it here?
30 centimeter.
30 centimeter. Yeah, that's correct. So, how you have calculated? So,
This time the disparity directly proportional to baseline.
baseline, yeah,
So
correct.
d2 upon d1 is equals to b2 upon b1. So we can get this 10 multiplied by 36 upon 12. So we get 30.
Yeah, correct. So, it is again based on this concept again, Z is equal to F into B divided by D, right? So here the depth and baseline, we need to find the relation between the depth and baseline. So already we know that the depth is directly proportional to B, right? Baseline, here a relation between the D and B, sorry, disparity basically. So just I go little bit more. So Z into D is equal to F into B, right? From here we can calculate. So that means D is directly proportional to B already. So here we can assume that the focal length and object depth that is remains constant. Okay, so here. So from here it is a constant. So just B1 is given, D1 is given, again D2 is given, and we need to find out the B2. Okay, so now we can express it by this equation like V1 divided by D1 because it is a directly proportional, B2 divided by D2 directly. Already here B1 is given, that is 10 centimeter, D1 is given 12 pixels, D2 is given 36 pixel. Now we need to find out B2. So from here directly if you put, you will get all answers. So 10 by 12 divided by 36 divided by B2. Okay. So now if you calculate here, so you will get 12 into 36 divided by 10, right? Is it fine? Something is there. No, no. B2. So here it is a bit little bit wrong. It is here. So yeah, 10 by 12. So here it is a V2 by 36, right? So from here you will get V2 is equal to 10 into 36 divided by 12, right? So V2 here you will get 30 centimeter. Is it fine to all of you others? Are you able to understand this question? Is it fine? Okay, so now we will solve the another one, 23. An object is 200 centimeter tall. It is located at an average distance of 10 meters, that is 1000 centimeters, from a camera with a focal length f is equal to 50 millimeter. What is the height of the object in the image? Okay, 1 centimeter, yeah, correct. But how you have solved this question? To 1 centimeter?
Magnification is equal to focal length by
Okay,
average depth. So from that we calculate magnification, right?
okay,
It
yeah,
is 5
correct.
by 1000, then multiply by 200 centimeter. So we will get the actual image size.
Yeah, correct. So already we know that the magnification is represented by the image height divided by object height, right? And that is also here object height, it is a 200 centimeter, and it is also the located at an average distance of the 10 centimeter from the camera and focal length. So from that one, from magnification formula, directly you can calculate, that is h image height is equal to h object height, and that is also equal to f divided by z average, right? So if here we need to calculate the height of the object, that means h object would be equal to h image into z average divided by f, right? No, something is to see here. We need to calculate of the object in the image. So this one we need to calculate. So here h image actually we need to calculate, that is equal to f into h object divided by z average. So just we need to put f is 50, it is given, or you can say 5 centimeter because we need to calculate in centimeter. So yeah, 5 centimeter it is given, and multiplied by 200. The object is 200 centimeter tall, and z average that is given as 1000 centimeter, right? So if you multiply the upper one, so here it is also 1000, 1000. Overall, you will get 1 centimeter here. Is it fine? To other one, can we move to our next question? Actually, two more questions are there. So just moving to other. If anyone has any doubt, so you can just ask. Is it fine? Okay. So now moving to our next question. Next two more questions. So next question is, a point in the world is located as PW. It is 100, 50, and 20. The camera is rotated such that its rotation matrix R is identical matrix. There is a no rotation, but it is translated by this value -100, -50, and -20. Then what is the location of a point in a camera coordinate system? So as we already know that the relation
Origin.
between yes, so please,
Origin is the answer, right?
yeah, correct. Origin is the answer, because already we know that PW plus T. R is the rotation matrix, T is the translation matrix. Here, our rotation matrix R is the identity matrix, right? It is given. So basically, it will be the PW plus T. So PW it is given as, I mean, 100, 50, and 20 plus, and it is given -100, -50, and -20, right? So if you just add this, you will get 100 minus 100 will be the 0 only. 50 minus 50 will be 0 and 20 minus 20 is 0 only. So it is the origin itself. What is the location of the point of the coordinate camera coordinate system? PC will be the 0, 0 and 0. So this one is the answer for this one. So our next and last question is for a function fxy representing a filled circle of radius r is 10, amplitude is 1. What is the radon transform value 0 theta at exactly rho is equal to 10?
0.
Yeah, correct. It is a 0. So how you have solved this question?
The same formula last time we used 2 into amplitude square root of r square minus rho square.
Yeah, correct.
Because r and rho are equal, they just become 0.
Yeah, correct, correct. So it is again 0. So already we have seen the formula previous one also for the if the rho is passing with the radius of 10, so rho theta. The formula it is 2 into amplitude root of r square minus rho square. So amplitude here it is given 2 into 1 r square, that is 10. It is a 10 square. Again rho value is also 10. So 10 square minus 2, so it will be the cancel out. So here you will get 0 only. Okay. So these are the questions for this week. So now if you have any doubts, we can discuss. Otherwise, we can close this session. So thank you everyone. Thank you for joining this session. Now if you have any doubt, you can ask. Otherwise, we can close the session. Okay, so is it helpful for you guys? Is it fine?
Yes, ma'am.
Okay, so someone is asking question number 24 and 25. So you have doubt in these questions? Yeah. So you can, yeah, it will be shared in the portal. So yeah, this is a link from where you can access all the YouTube video documents as well. So yeah, Saron, you are asking about question number 24 and 25. What is your doubt?
Ma'am, there's no doubt. I just need to copy. That's why. Thank you.
Okay.
Thank you, ma'am.
Okay. If you have any doubt, you can ask. Otherwise, you can leave the session.
Ma'am,
Yes.
I did not get the inverse radon using Fourier. I tried to follow sir's slide but could not understand it. Could you just
Uh,
give me a brief conceptual explanation of what it
okay.
does?
Okay. So Saron, is it fine for you? Can I change the slide?
Yes, ma'am. Yes.
Okay.
Thank you, ma'am.
Yeah. So yeah, you are asking which question?
Not about the question, about the inverse radon using Fourier transform.
Inverse radon. Okay, you want to ask about that
Yeah,
whatever sir has discussed in the class.
yeah.
Okay, so actually I need to check also. So I have gone through the questions only. So what they had told in the in the class, I didn't go through that. Okay, let me just available in the next week. So I will go through that one and will let you know. Okay. So inverse Redon transform. Yeah, you are asking about.
Yes, yes.
Okay,
There's
okay.
a
So,
concept. Yeah.
okay. So I will go through that one. And so what is the doubt on that?
Not a specific doubt about the mathematical formulation in general. Like, I could not understand that.
Okay. Okay. So I will let you know in the next class because for this week I didn't go through that. What they told.
Thank you. Thank you, ma'am.
Yeah. Okay. Okay. So anyone else? Anything? Any doubt? So can we close this session? If you don't
Yes,
have
yes,
any
we can.
doubt, yeah, yeah. Okay. So thank you everyone. Thank you for joining this session. Now I'm closing this session.